Hello, welcome to this workshop on momentum and impulse. Let's get right into it. So, momentum deals with collisions, and with collisions, we need to check what was happening before the actual collision took place, how fast cars were traveling if they were cars, and how much their masses are if they are cars or whatever objects that are in question. Then we know that whenever collisions happen, right, momentum is conserved. So we need to take into account the conservation of linear momentum. Then once momentum is conserved, we can represent that by using this formula here, right? The sum of momentum initially is equal to the sum of momentum finally. And this in more detail is m1 vi1 plus m2 vi2 is equal to m1 vf1 plus m2 vf2. That is the formula for conservation of linear momentum. Now there's some stuff that is happening during a collision as well, right? And we need to take into account what? Impulse. And impulse is what? Given by this formula. If net delta P is equal to if net delta T is equal to delta P, that is the change in momentum. That is impulse. Now, linear momentum is given by P, and its SI unit is kilogram meter per second. Momentum is a vector. In our questions, we need to choose a positive direction and a negative direction. Now, impulse, which is F net multiplied by delta T, is also known by this SI unit in Newton second, because force is newtons and time is in seconds. Now, impulse is a vector. It is a force acting over a period of time, and it is equal to the change in momentum in the positive or negative direction. So, let's say we are an object here, right? And where are we going? We are going to the left. Let's quickly do that. So, this is where we are, and we go to the left. We stop at 4, right? So, our momentum here is 8 when we start, and here when we end, our momentum is 4. So the change in momentum there would be the final minus the initial, and that will leave us with minus 4 kilogram meter per second. That is what? The change in momentum. So if we were going to the right, we would have the same thing. Now it just means when we go to the right, we're going to have a positive 4 kilogram meter per second, and this just shows you that here it will be positive because of the direction that side, and that is the impulse. Remember, it's the change in momentum. Now, since linear momentum is conserved, if there are two objects, the momentum gained by one object is equal to the momentum lost by the other object. Remember, this is always a closed system. You cannot have momentum escaping. Due to Newton's third law, the force of A on B is the same as B on A. Since a collision is a contact force, the change in time is also the same for both objects, since A touches B only when B touches A. Thus, the impulse, or F net delta T, is also the same for both objects but opposite directions. Now, let's look at this example here. Object A with mass 200 kg is moving west at 10 meters per second. Object B with mass 100 kg is moving east at 15 meters per second. The objects collide and are in contact for 0.1 seconds. After the collision, object A is moving west at 2 meters per second. Now let's see what they want us to do. They want us to fill up this table there, or complete the table. Let's try to do that. What is the initial momentum of A? We know momentum is mass multiplied by velocity, right? So let's take west as positive, and then we'll take east as negative. Now this just means the initial momentum of A will be 200 multiplied by 10, and that gives us 2000 kilogram meter per second. Right, that's the SI unit for momentum. Then for object B, its initial momentum will be 100 multiplied by 15, but in the opposite direction. So that'll be negative 1500 kgms. Just like that. The negative just tells us about the direction. Now we need to find the final momentum. Now we can easily find the final momentum there. by using m1 u1 plus, let me just go back, my slide just went forward, so it's m1 u1 plus m2 u2 is equal to m1 plus m2 moving with one velocity. So u just stands for initial velocity, right? Now we can easily find what velocity they are moving with. So we know that the initial momentum, right? Remember, this is the initial momentum of A. So I'll just say it's 2,000 instead of even doing the calculation again, right? Minus 1,500 for the momentum of B. This is equal to 200 plus 100. The mass is 200 plus 100 with one velocity. Now on the left hand side, we are going to have 500 is equal to 300 V. Then let's quickly find what V is. Then V is equal to 1,7 meters per second. There we go. Now we can find the final momentum of A. How do we do that? We just take 200 multiplied by 1.7. Let's quickly do that on our calculators. So that'll be 200, its mass, multiplied by 1.7. Now this is just going to be 340 kgmas. Now we need to find the final momentum of B, and that is just going to be 100 multiplied by 1.7. That is 170. There we go. Now it's quite easy for us to find the change in momentum. And how do we do that? The change in momentum is equal to the final momentum minus the initial momentum. So let's quickly find that on our calculators. That'll be 340 minus 2,000. Let's quickly do that. And that is 1,660. Let's do the same for object B. 170 minus a negative 1,500. And that is just going to be 1,670. Then what is the impulse? Remember, the impulse is the change in momentum. So it means that the change in momentum is equal to the impulse. So we can just say that's 1,660. Copy those values, put them here. Those are the same thing. Right. Now, what is F net? Remember, F net delta T is equal to the change in momentum. Then we can divide both sides by change in time. Now we can find, so these will cancel, so we can easily find F net by saying the change in momentum over the change in time. So it'll be what? 166, that's supposed to be a 0, right? So 1660 divided by 0,1. Let's do that. 1660 divided by 0.1, and that gives us 16600, 0. Then we need to do the same thing for B, right? So that'll be 1670 divided by 0.1. 1670 divided by 0.1, and that gives us, quickly write that down, 16700, 0. And there you have it. Now let's carry on. So let's look at linear momentum, right? So if we look at this table here, right? So we have velocity versus momentum, right? Let's see how they affect each other, right? Because it's linear momentum, right? As the velocity increases, the momentum would also increase, right? They are directly proportional to each other. Now, with kinetic energy, because as we go to the right there, right, as the velocity increases, right, because there is a squared there, this is how it affects the kinetic energy. So, as the velocity increases there, the kinetic energy also increases, but it's not a linear graph, it's exponential. Now let's look at this example. A truck is moving with a velocity v and kinetic energy of k. The velocity is now tripled. What is the new kinetic energy of the truck in terms of k? Let's see what we can do there. They didn't give us any units, but we should still be on the right track. Let's see. Truck is moving with a velocity of v and kinetic energy of k. So let's look at the kinetic energy. Ek is equal to half mv squared. Now we know that its kinetic energy is k. Now they're saying if the velocity is now tripled, so let's see what would happen if the kinetic energy, if the velocity is tripled. So this will be a new kinetic energy. A half, the mass is still the same, the velocity is now tripled. Tripled just means 3 times v, and we need to square this. So this means we have half m9v squared. So we can just start with the 9 and say this is 9 into 1 over 2 mv squared. Right. Now, as you can see, this guy here is the same as that one there. But now there is a 9 in front. So what happened? Right? So it means that it was multiplied by 9. So in terms of k, it's just going to be 9k. Let's carry on.